Use AVSChain, and we'll go over how it works right now. So AVSChain supports kind of a app chain kind of rollup, which can take any kind of app specific execution environment. So for in this case, the example is a simple token transfer. So we can go through the execution method that has been given up. So we have included the mint and the transfer along with the operations that is required for the rollup as well. It is defined inside separately so that the AVS operator can have any generalized form of operations inside it. Now, this is transferred to the sign and respond to task. So, how the storage is stored for the rollup is like the form of a JSON file. So, you can see there's a genesis.ts that will form the genesis file. So, if we go to this can form a genesis file or the initial storage for the rollup, which is given up in the IGDA layer. If we go to index.tsx, we will find that the sign and respond to task first figured out the previous state from the IGDA, then executes the methods based on the state machine that has been given up by the user. And after the state has been updated, it is posted back to the eigen layer, and then the transaction is processed back to the L1 contract. So the L1 contract also takes up the previous request ID and the request ID, the current request ID, which is required to get the previous state and the current state of the rollup from the eigen layer. So anyone can verify the current state of it. Now we will say an example. We can start off with minting a token. So we have sent a transaction which is there, and we will wait for the operator to take up the transaction from this. So we can see the mint transaction has been taken up by the operator, and we can see we fetch the previous state, which is this from the IDNDA using this request ID. And after that, we have updated this state with this transaction, and we can see the updated state with 98 and plus 100 minting of tokens. So this is updated inside the sequencer. So we got a soft confirmation from the sequencer right now that the transaction has been included and the state has been updated. Now we wait for the updated state to be posted to the IGN DLA. Now we can see the updated state has been posted to the DLA finally, and we have got the medium confirmation from the DLA as well. So from the sequencer as well. So that means the sequencer can no longer change the current state. And it has been posted along with the request ID to the DLA. And finally, the state has been updated using the request ID in the smart contract on L1. So the hard confirmation we have reached for the rollup for this transaction itself. So if you can see, this request ID corresponds to the updated state inside the eigen layer, and the previous state ID request ID corresponds to the previous state, which is itself which can be verified by any other user. We can start off with another transfer method, which will function the same way. Now we can see it has taken up the transfer method from this account to this account. We can see it has got the previous state from the eigen only. And if we see, it has applied the state, so 10 tokens have been transferred to this address. Until this works, we can go over the code base once again. So if you see in the contracts also, in the contracts we have mapped the current ID and the previous requested ID so that the user can take up the previous and the current state. And for the DAD layer, we have seen that we can query using the requested ID and to get the state and post using this. And the DA service has been running inside this. So we have a DA client written in Go having the IDNDA packages, Go packages. So we got methods for submitting the blob handler and getting the blob uh, details from giving the request ID. So if we see, oh, this is still going on, maybe we can figure out the short proof method as well. So there's a basic transaction flow which we have seen. I think I will pause it out to let anyone go through. For the next short proof mechanism, if we can see if there is an honest validator, it can fetch the previous and the current request ID and get the previous and the current state using the same previous request ID and get the user transaction trace, which means this current thing that has been emitted by the service handler, that whatever the method has been called with whatever data. So once that has been done, the honest validator can re-execute, and if invalid, it can challenge the entire in the stake contract, telling the operator has been malicious, and that can slash the stake of the validator itself. So that's how the whole thing is done, and we can see the transaction has also been completed. Maybe we can check it out on here. So it is called the service manager contract, and it has been doing stuff as well. So that's now we can see the logs also. It has been kind of broken, so I think the logs has been working. So how does this actually can be? As I said, the operator as such is not confined to a particular machine, state machine logic or something. As we can see, it has no logic inside the operator itself, but the logic is separated between the executor and the operations. The execute method can take up any operations that has been defined in the operation section and executed based on certain operator based on certain method names. It can do pre-hooks and post-hooks and execute it without converting into any other language like WASM or any other bytecode to operate during the operator environment. It can do anything inside it, and we can also make async calls. Like we can also make API calls as well. So this creates a kind of a better app specific rollup. It can be written in any general purpose language, JavaScript, as in the example right now. So yeah, that's about the AVS chain, and I hope you like it.